at the University of Buffalo, the State University of New York. So Igor received his PhD in theoretical physics at the University of Minnesota in 1998. So he's working on several topics, from spin transport, superconductors, Majorana fermions, magnetic semiconductors, proximity effects, and two-dimensional materials. So his predictions for spin devices, not limited to magnetoresistance, so such as spin photodiodes, transistor lasers, so have been experimentally realized. And also Igor is a fellow of the American Physical Society. He received in 2006 the National Science Foundation Career Award, and in 2019 State University of New York Chancellor's Award for Excellence. Okay, so Igor, again, thank you for being here. And I guess now everyone wants to hear from you. No, sorry, before I give you a word, so to everyone, please make sure that your microphone is muted. So, and still anyhow, feel free to ask questions to Igor. And okay, so that's all. So please, Igor.
Thank you. Yes, thank you very much, Marco. Thank you everyone for coming to this presentation. I also appreciate this opportunity, because very often these geographical distances are making seminars more difficult, but maybe COVID situation brought us closer from different parts of the world. What is shown here is basically Niagara Falls. So this is very close to Buffalo. And on the left side, it's not visible. There is a monument to my very, very distant relative. His name is Nikola Tesla. But unlike him, I'm a theorist, and I have a hard time even changing a light bulb. So no practical skills. So this work has been a result of collaboration with my group and colleagues at Buffalo. And also it involved some experimental groups. And what I would like to just share with you is basically the outline of the presentation. And after introduction and motivation, I will then discuss a little bit about proximity effects. First, I will start with magnetic proximity effects, and I will focus on different classes of materials with weak and strong spin orbit coupling. And then I would consider what happens if also superconducting regions are involved. And one motivation is that one can engineer unusual properties, including so-called Majorana fermions. And then I will discuss a little bit about a possible topological superconductivity that has been detected, and such topological superconductivity is known to host Majorana fermions. And then I will provide some conclusions and outlook for future work. Lots of these things are connected to work at NTU in terms of considering 2D materials, and also in terms of spintronics, which is connected to these spin and magnetic effects. When one talks about spintronics, it's a combination of a relatively novel name, started in 1996, and much older physics. For example, anisotropic magnetoresistance dates back to 1857. Most of the success in spintronics relies on well-established magnetoresistive phenomena. So what would be interesting, and maybe we'll be able to discuss it in this presentation, is that there are applications in spintronics that are not limited to magnetoresistance, where proximity effects could help. So if I go a little bit back in history, in terms of motivating this work, those of you who have studied spintronics for a while, you may remember that there was a significant interest in class of materials called magnetic semiconductors. And specifically, one motivation was that maybe they can combine storing information that is well established with magnetic metals and processing information which is well established with using non-magnetic semiconductors. So basically the hope was that maybe 1 + 1 these two separate functionalities could actually be greater than 2, that somehow magnetic semiconductors could bring best of both worlds together. This actually did not materialize. So maybe a better inequality would be not 1 + 1 greater than 2, but actually 1 + 1 less than 1, because magnetic semiconductors were not that great magnets, and they were also not that great semiconductors. Nevertheless, as a test models, there was opportunity to really study, at least in principle, novel phenomena, controlling by electric field Curie temperature or coercive field, first demonstration of tunneling anisotropic magnetoresistance, or first experimental demonstration of spin-orbit torque. So while they were not particularly useful for practical applications, some novel phenomena were discovered in these materials. And the reason why I'm mentioning that, because idea of transforming materials through doping is something that is well known, not just to semiconductors, but many other classes of materials. But here we see that trying to get magnetism to semiconductors comes at a price. For example, gallium arsenide is a well-known non-magnetic semiconductor, and it could be made magnetic by adding manganese. However, it comes at a cost of about 1,000 times lower mobility, a large contribution of disorder, transport is very, very poor, and also poor optical properties. While there is an excellent luminescence in gallium arsenide, it is completely suppressed in gallium manganese arsenide. So this is just a general maybe lesson or a message that even though we often rely on doping to transform large class of materials, this doping comes frequently with a cost. So what would be nice is to discuss perhaps a different approach to transform large class of materials, and a motivation for that could be summarized with this simple statement that grass is greener on the other side. In our case, this means even when we have interesting material, we usually would like to modify it. If we have silicon, we would like to dope it or change it somehow to make it useful. So let's start with this layer A, and let's modify it, not by doping, but by choosing carefully its neighbor. So this layer B could be a magnet or superconductor, and we may even have a layer C. So as a result of these neighboring layers, layer A may be transformed. It may inherit properties that are completely different from any of those individual layers. So by proximity, by leaking of these materials properties in layer A, we may establish new phenomena, and we may even have topological protection. So topologically trivial materials through proximity may become topologically protected. And here schematically you can visualize this in analogy to a knot. Even when you move a knot, at least its ends a little, it will not change whether a knot is there or if it's absent. So this signifies that topology and the properties that we are able to introduce are global, and they may not depend on disorder or local perturbations. So this is basically then a kind of a summary or objective that proximity effects, which have been studied for many, many decades, now can be viewed more broadly, not just as a collection of isolated and curious phenomena, but as a systematic tool to transform large classes of materials. So before going into proximity effects, let me remind you about some basic aspects of superconductivity, because in case of superconductors, we had a first situation of studies of proximity effects. So here is a kind of simple summary where one can contrast normal state and its excitation spectrum, where around Fermi energy I can reflect whole part of the spectra to make it positive in energy. And then if I zoom in at its dispersion close to the Fermi wave vector, in the superconducting state, I realized that there would be some gap, that there wouldn't be excitations allowed for arbitrarily small energy. And then we distinguish hole-like and electron-like properties, but unlike in the normal state, the corresponding charge of these excitations is actually fractional. If you look at the density of states, in addition to these normal excitations, we also can talk about states that are available at the Fermi level at zero energy. These are Cooper pairs, where pairs of electrons can form a bound state, usually a spin singlet. So with this a brief introduction to superconductivity, we can go to see a first example of proximity effect. And this is actually rather old. Meissner, from famous Meissner effect, already in 1932 had seen that if two superconductors are separated by a non-superconductor, a supercurrent can flow in such structure. In other words, about 30 years earlier, he discovered Josephson effect. So he basically realized that superconductivity can leak into neighboring non-superconducting regions. So this normal metal then acquires superconducting properties of its neighbor. And what is nice about superconductivity is that we have a microscopic picture how such proximity effect can take place. So here is a normal metal, here is a superconductor. There is, of course, simple ordinary or specular reflection where electron is reflected as an electron, but there is also peculiar so-called Andreev reflection where incident electron at an interface is reflected as a hole, and this hole retraces this original trajectory. If you look at the conservation of charge, this electron being reflected as a hole effectively means that two charges are transferred across the interface. So this is now allowing us to form Cooper pairs. This is allowing a transfer of superconducting information and also of flow of current without any resistance. What is interesting is that this reflection now mixes electrons and holes. So charge can be changed in such scattering processes. And this physics has been used also to explain phenomena in very different areas, like Hawking radiation of black holes or some confinement effects and flavor effects in quantum chromodynamics. In addition to superconducting proximity effects, we also have magnetic and spin orbit coupling effects. However, unlike in the superconducting case, these effects are very, very short range. In superconductivity, this leaking of superconducting properties can exceed a micron. But when you talk about magnetic proximity effect, it can be very short, just 1 nanometer. And with this short length scale, the question is, why would we care? This is something that is so short that maybe related perturbation is negligible. We really do not have to worry. This is where two-dimensional materials come into play. And of course, we know there is a growing class of two-dimensional materials from well-established graphene with weak spin orbit coupling to, let's say, transition metal dechalcogenides with very strong spin orbit coupling. And with their atomically-thin structures, even 1 nanometer is no longer negligible because 1 nanometer exceeds thickness of atomic layers. So if you look now at this scheme, if I place a ferromagnet next to graphene, this ferromagnet will transform pristine graphene and Dirac cone will be a spin split through exchange splitting. So if I was to send current, this current will be modified and transport properties will be modified because of this induced exchange splitting, and I would be able to even detect such spin polarized transport using another spatially separated ferromagnet. So the point is that as soon as we have two-dimensional materials, what may otherwise be negligibly short length scale for proximity effects is long enough, and such materials can be completely transformed with proximity effects. So here is a simple proposal how one can change properties of graphene by placing a ferromagnet, metallic ferromagnet close to graphene. We don't want to have chemical bonding, so one can put dielectric, let's say, another layer of graphene or boron nitride. And what is actually interesting is, based on the gate voltage, we may be able to change how much of magnetic proximity effect leaks into graphene. So this red color signifies spin polarization that is proximity induced, spin polarization of density of states. And by applying gate voltage, we can control that. But what is interesting is we can not only control magnitude of spin polarization, but we can also control its sign. So a simple magnet now allows us to have tunable, gate-tunable magnetic proximity effects. And then there are some ideas how possibly such phenomena could be used for novel spin transistors and spin logic. So if I try to illustrate this a little bit further, I'm looking now at first principles calculation, where I have graphene symbolized here with two inequivalent carbon atoms separated from standard ferromagnetic metal, cobalt, by a layer of boron nitride. And what is shown here is that as the gate voltage is changed, there would be changes in the proximities-induced spin polarization. When I go far away from Fermi energy, I can see large changes, but they are not very relevant because transport in these structures is determined by what happens at the Fermi level. Nevertheless, at the Fermi level, I can see that by changing gate voltage, it is possible not only to change magnitude of proximity-induced spin polarization, but also its sign. And another thing to realize is that to have this tunable magnetic proximity effect, where spin polarization can change both sign and magnitude, it is crucial to have van der Waal bonding. So if you think about chemical bonding, it's a little bit like a superglue. You put two materials next to each other, but then there is no hope that somehow you can tune them or kind of alter their properties unless you destroy them, unless you break that bond. But with van der Waal bonding, it's almost like if you have a post-it note. We have some feature in energy here, and if we apply gate voltage, this feature can be moved back and forth, just as it's shown here by field shifting of Dirac-Cohen. So establishing van der Waal bonding then gives us more flexibility with proximity effects, because then they can become tunable. And indeed, this prediction for tunable magnetic proximity effects has also then been supported by by a group of my collaborators in Ohio State. And then there was another experiment, this one involving Andre Geim, where they have also seen that one can change by gate voltage effective spin polarization. Okay, so let me now switch gears, and from this material which has very weak spin orbit coupling, let me go then to—
Hey, Igor, could I ask a quick question?
Please,
so in these experiments, how do they determine the spin polarization? So you said they could change it
yes,
by gate voltage, right? So how do they determine it?
That's a very good question. So maybe you are familiar with the concept of spin valve and so-called lateral or non-local spin valves.
Ah, so I see. Okay.
If one expects this proximity effect, it should also modify spin transport. And one could then see basically a different induced spin polarization that is probed by the other ferromagnet.
I see.
But my colleagues at Ohio State had designed these 1D contacts where basically graphene has this one-dimensional rather than two-dimensional contact. And this was important because if we place two-dimensional contact, if we place metal next to graphene, there may be a large shift of the Dirac cone, and then we may not be able to tune it close to the Fermi level and have some large changes. So it's important to have partial decoupling of the ferromagnetic metal and graphene. Okay. And what is then maybe intriguing is rather than switching direction of magnetization by applying magnetic field or some other technique, we may now be able to replace that by changing gate voltage and effectively changing proximity-induced polarization. So as a concept, it is interesting because we have electric means to control spin polarization, but it doesn't rely on spin-orbit coupling.
I see.
Does this help?
Yeah, I think it helps. Thanks.
Okay. And please feel free to ask more questions. So let me then move to transition metal dechalcogenides. So they are in the opposite limit. They are materials with strong spin-orbit coupling. We see here this characteristic spin valley coupling such that optical transitions are helicity dependent and they switch from one to the other valley. Here, what is shown for simplicity is very, very small splitting of the conduction band. It is not negligible, but it's small, and much larger splitting of the valence band. So we can then talk about A or B excitons, which have different energies, different wavelengths. And these excitons now tells us that we need to include Coulomb interaction. In many cases, Coulomb interactions in spintronics are not that crucial, and most of the proximity effects are exclusively studied without Coulomb interaction. We just worry about single particle picture. This is not such situation. We see from this spectra that optical features are dominated by excitons, whether neutral or charged, and it is really essential to include these strongly bound features because binding energy of such excitons can be as large as half an electron volt. So then there is a basically question, what happens if in these materials, transition metal dechalcogenides, we consider magnetic proximity effects? And this is what has been done by my colleagues. So my colleagues at Buffalo perhaps were one of the first groups who studied influence of magnetic substrate, europium selenide, sulfide, here ferromagnetic insulator, on a monolayer of tungsten diselenide. So for comparison, if a substrate is non-magnetic, there wouldn't be much of splitting in the observed reflectance spectra, even at 7 Tesla. And this splitting becomes much larger when one considers magnetic substrate. So you can see this valley splitting that is rather large. This valley splitting, so maybe just to go back to the previous case, is important because if we recognize that we can take advantage of spin degrees of freedom in transition metal dechalcogenides, it would be nice to remove this valley degeneracy. Just like if we are trying to look at spin-dependent or magnetic effects, it would be nice to have non-zero spin polarization to introduce, for example, by non-equilibrium processes or equilibrium processes some imbalance between number of spin up and spin down carriers. So removal of valley degeneracy is very appealing property. And here they have demonstrated this was indeed possible. Magnetic field has a role in europium sulfide, not to magnetize it, but basically to align magnetization in the appropriate direction so that optical selection rules would allow measurement of this spin splitting. And this valley exchange that was measured optically then agrees also with the normal component of magnetization at low temperature before this material becomes paramagnetic. So what is very interesting is clearly we are in the limit of strong Coulomb interaction, which makes excitons possible, and excitons are fingerprints of this magnetic proximity effect. And yet, about 40 or even almost 50 years since first magnetic proximity effects were studied, it seems in no material they have been analyzed using Coulomb interactions, so accurately considering what happens due to Coulomb interactions. Or in other words, all the studies of magnetic proximity effects in any material were limited to single particle picture. So this is then what we wanted to change. We wanted to check what happens if we consider Coulomb interaction. And at that time, we felt that this was really missing, that maybe we were the first to consider. And now the picture is shown similar to this previous experiment. We have a monolayer transition metal decalcogenide, and there is a magnetic substrate. Magnetic substrate can have magnetization in different direction, and what is shown here is typically considered as boring, because what one would like to do is to remove valley degeneracy, as I mentioned. So in-plane magnetic field would not do that. In-plane magnetization will not do that. So unless you pull it out of the plane, it's seemingly nothing interesting happens. However, we wanted also to look at these boring cases. We wanted to check for all sorts of direction of magnetization what would happen. And here on the right, I'm showing so-called dark excitons. So this is now electron-hole pair of the wrong spin orientation, which would be optically forbidden. So it would not contribute to light. And you can see here these opposite spins. However, if we were to change direction of magnetization in the substrate, then interesting things happen. Not only the spin splitting in a conduction and valence band will change, but direction of spins will also change. Now you can see that what was optically forbidden may start to become optically allowed. In technical terms, these dark excitons can become bright. And what is basically then possible is that we can, by changing direction of magnetization, transform optical selection rules and optical properties of the material. So let's go now to compare this more general situation, not just magnetization pointing out of plane, which people thought was the main important thing, but also some other cases. Here in the inset, what is shown is absorption spectra using single particle picture. This tells us how this single particle picture is indeed inadequate. We don't see any excitonic peaks, so we would not really be able to establish correspondence with the experiment if we exclude Coulomb interactions and the physics of excitons. If we look at non-magnetic substrate, no magnetization, then we get, using this Bethe-Salpeter equation, expected A and B excitons, which I mentioned. If we then go to out-of-plane magnetization, which is focus of most of the studies, we also see expected behavior, exciton will split, and splitting of A and B exciton will be opposite, just as it's seen in the measurements of our colleagues. But what is interesting, if we go to this seemingly boring case of in-plane magnetization, we have now a new feature. And this new feature can be viewed as dark exciton. So we are able to brighten the dark exciton and have this new spectral property. So in other words, just a simple change of direction of magnetization can strongly change optical spectra and give us even previously unexplored features. So right now I have studied these materials that are topologically trivial, but maybe an important question could be, can we from optical properties also deduce non-trivial topology? So in other words, is there some good optical signature of topological properties? In transport, of course, answer is yes. And from integer and fractional quantum Hall effect to many properties of topological insulators, they have really been extensively studied through transport. For optical properties, this is not that clear. And what is shown here is one proposed scenario that we had in mind. So what we would like to do, we would like to obtain tunable band topology such that by changing electric field, we may change helicity of the emitted light. So this change of the helicity of the emitted light would be intricately connected to the topology of the material. So let's see how it works. And let me give you a little bit of motivation. So some of the atomically thin materials can be a very, very robust topological insulator. So a few years ago, there was a discovery of monolayer bismuthine on silicon carbide, which has a huge topological gap, 0.8 electron volts, about 100 times more than famous mercury telluride, where first quantum spin Hall effect was measured. However, this material, even though it's an outstanding topological insulator, has indirect gap and no Valley effect. So for our purposes, it's not very helpful. So what we wanted to recognize is that maybe there is a possibility to design our structure such that by applying electric field, we may reverse ordering of the conduction bands in one of the valleys. If that happens, then there would be a change of so-called winding number, topological number, which a few years ago has been indicated to be connected to the changes of optical properties. So for example, if you consider bilayer or trilayer of graphene, then there may be different winding numbers associated with them. So people knew in the past that different systems could be characterized by different winding numbers. What we did instead, or what would be our goal, is not to consider different systems, but to have a single material where by gate we can tune its properties, change corresponding winding number, and basically change the helicity of the emitted light. One possibility would be to have magnetic substrate, or maybe one can add magnetic dopants, and we focused on antimony, hydrogenated antimony doped with tungsten, because we have inequivalent SB sites. Then effectively, in addition to standard terms in Hamiltonian, hopping, intrinsic spin orbit coupling, or Rashba spin orbit coupling, or even exchange field, there would also be a staggered potential, which could be further tuned by electric field. So if we now consider what this means at the single particle level, by applying electric field, we can create band crossing not at K, but at K prime value. And this single particle picture, which changes as a function of electric field and also may depend on this on this potential, staggered potential, we can confirm this by calculating more rigorous Bethe-Salpeter equation. So here we have absorption spectra, and depending on the magnitude of the electric field, our low energy exciton can have positive or negative helicity. In other words, on the same sample, simply by changing electric field, we are in a position to reverse helicity of the light. So the change of Bain topology, which leads to change of the winding number, can then be measured experimentally by looking at the changes of the bright exciton. So this is exciting possibility because now well-established optical tools can also allow us to probe topological properties. So with this, I would like to switch to structures that will also involve superconducting regions. If maybe there are questions about this part, this would be a good point. If not, I will then continue with discussing superconducting properties.
So I had a quick question here. So how can you tell that actually there is a change in band topology? And in particular, what do you mean by change in band topology? Do you mean going from Z2 non-trivial to Z2 trivial?
So let's look at this structure. So here, by band topology, I'm talking here about ordering of the, let's say, conduction bands. And here in the K prime valley, this ordering.
Oh, I see. So you just mean the order of the spin-orbit coupling.
That's right.
That's
so
all.
I have not, let's say I'm in a topological insulator. I'm not closing and opening the gap. I'm just changing ordering of the conduction bands. And even though this seems like a minor effect, it can be very profound because it transforms optical selection rules and laws for the emission of light.
Of course, yeah. Okay, I think I understand now. Thanks very much.
And what we were excited is that unlike in many other cases where these changes would imply comparing sample A and sample B, we can do it in a single sample, at least theoretically, based on tight binding, Bethe-Salpeter, and first principles calculation. So this is now just maybe an early example, but I think more of them will follow because the topological properties could be imprinted in these selection rules, and the structure and behavior of exciton may reveal this topology. Okay, if there are no questions, of course, you're welcome to ask more towards the end of the talk. Let me try to then argue why adding superconductivity could be of interest. On one hand, there is a possibility to introduce these exotic Majorana states where some people are excited because it can be used for fault-tolerant quantum computing and some fascinating phenomena. On the other hand, it can be maybe more elementary because superconductivity for many decades was part of spintronics, and maybe we can engineer not spin singlet, but spin triplet superconductivity, which is very elusive in nature, but maybe relatively robust in superconducting junctions. And if we have this equal spin triplet, then we may also have dissipationless pure spin current. So we may be able to do some interesting things that may not be as easy in the normal state. For topological protection and kind of designing topological structures, we try to introduce something that is maybe too good to be true. Rather than designing nanostructures by epitaxy, let's say in molecular beam epitaxy, we suggest that we can design or define nanostructures by placing magnetic textures. By having regions of inhomogeneous magnetization, we may be able to create effective wires and obtain some interesting properties. So this is one motivation. And the other one is perhaps more practical. When spin-orbit coupling is present in the system, if it's not strong, usually it can be neglected. So we know that spin-orbit coupling is behind perhaps first element of spintronics, this so-called anisotropic magnetoresistance from 1857. But there are many systems where in the normal state, spin-orbit coupling is small, and the tunneling analog of this anisotropic magnetoresistance is negligible. Here, it's just tiny part of 1%. What is remarkable that once this structure is cooled below superconducting temperature, rotation of magnetization gives orders of magnitude larger magnetic anisotropy. So this was our theoretical prediction 5 years ago, and now it has been confirmed experimentally. In other words, if one goes to superconducting state, yes, it will be possible to have spin triplet superconductivity, but in addition to that, it may be possible to amplify small effects of spin-orbit coupling. So superconducting state may become very, very sensitive to otherwise negligible contributions to anisotropy. Okay, so I would like now to switch and discuss this type of motivation of creating topological states through proximity, and then discuss why magnetic regions would be of interest, why one would be able to design nanostructures using magnetic textures. So here is a brief and very, very brief introduction to these so-called Majorana fermions or Majorana bound states. So basically, what is very intriguing is that exchanging these particles or states is unlike bosons and fermions, where we simply have change of phase 0 or pi of this relative wave function. These anyons are not simple anyons that are different from 0 and pi. It's not just some number, but basically they are non-commutative or non-abelian anyons, where we have effect after this exchange that is a little bit like matrix multiplication. And this matrix multiplication then tells you that such exchange could serve as a quantum gate, because when you put something in, after this exchange, what comes out would be different, just what we would expect in conventional logic gates. And key elements to realize these Majorana fermions are typically considered to be superconducting proximity, because needed spin triplet pairing is really elusive and very controversial in the existing materials, but through proximity, it can be created in superconducting structures, where then we also rely on the presence of strong spin-orbit coupling and Zeeman splitting. Most of the work has been done in semiconductor nanowires, typically 3-5 nanowires, indium arsenide or indium antimonide, and there would be direction for effective field due to spin-orbit coupling. There is applied field, and these Majorana bound states are existing at the region that is a little bit like a domain wall. It's between topological and trivial regions. So usually this would be at the end sketched here of a nanowire. And the signature for these Majorana fermions is often considered to be quantized zero bias conductance peak. As a side remark, we may have been first to predict that almost 20 years ago. However, these zero bias conductance peak can be tricky. They may occur for other reasons, not because we have Majorana fermions. And perhaps the most exciting aspect of having these non-abelian statistics is really not encoded in this zero bias conductance peak. So if we would like to exchange these Majorana states, we should really go away from one-dimensional geometry. We should try to seek two-dimensional platforms where this exchange or so-called braiding of Majorana fermions would be much more natural. So to this end, we consider the following structure. This is now standard S-wave superconductor. So just simple pairing of opposite spins. And next to it, we have a two-dimensional electron gas. So not a semiconductor nanowire, but a 2D platform. And above, we have arrays of magnetic elements. These magnetic elements can be spin valves or magnetic tunnel junctions. So relatively well-known parts of our hard drives or magnetic random access memory, where we know that depending on the direction of magnetization, parallel or anti-parallel in two ferromagnets, there would be a different resulting fringing field. And these fringing fields could modify this semiconductor region underneath. So what is shown here is a double proximity effect. On one hand, we have superconducting proximity because this standard superconductor would leak its property to the yellow region. And then from above, we have magnetic arrays, which through fringing fields would modify this yellow region. And we know that a result of fringing fields is not just simple magnetic field pointing up or down, but they are kind of non-trivial. They curve around. And these resulting fringing fields can then allow us to localize or even exchange or braid these Majorana bound states. So let's see how this works and how is this proposal connected and different from what is better known for one-dimensional structures. So first, let's try to understand why magnetic textures. At once, they provide needed ingredients for Majorana states. They provide Zeeman field. That's of course expected because we would remove spin degeneracy, but they also provide synthetic spin orbit coupling. So even if our material does not have spin orbit coupling, it can be effectively induced through these magnetic textures, and we may even create confinement. So what this sketch shows is that we can understand the role of these magnetic textures in homogeneous magnetization by rotating quantization axis along the direction of magnetization. When we do that, which is a standard trick in spintronics and other fields, so you can see references from many years ago, we can transform this simple Hamiltonian where in addition to kinetic term, we have some magnetic exchange. This magnetic exchange gives us effective magnetic field, and we may be able to simplify it by this rotation of spin axis. So we may just diagonalize it, and this term now, magnetic term, becomes simple. But as we make this magnetic term simple, we make kinetic term more complicated. And what we have as a result of this complication is effectively non-abelian field, or if you wish, synthetic spin orbit coupling. So the presence of inhomogeneous magnetization can allow us to design spin orbit coupling that may be needed to support these Majorana fermions. To compare how our situation is different from a well-established one-dimensional case of these semiconductor nanowires, it's good to recall what is the characteristic condition for establishing topological superconductivity or establishing Majorana fermions. We need Zeeman splitting that is large enough, that is larger than this combination of superconducting gap and chemical potential. In our case, we do not have this simplifying assumption that magnetization or magnetic field is constant and everything always point along one direction. We have magnetic textures, so we have to worry about effective derivatives of magnetic field. So we are going to have a more general situation, which then allows us to generalize this condition to our two-dimensional situation of inhomogeneous magnetization in fringing field. And what is shown is now an array of 9 spin valves or magnetic tunnel junctions, where a dot means magnetization pointing up outside of this plane, and X means pointing down to the plane. So we can change, and this is standard procedure in magnetic hard drives or magnetic random access memory, a relative orientation of magnetization in such magnetic arrays. And as we change them, we are also changing configuration of fringing fields, and we are changing respective condition that determines where topological state is present, or in other words, where we have topological and where we have trivial region. And the boundary between topological and trivial region is denoted here by this white contour. At the end, just as we were expecting in one-dimensional case of semiconductor nanowires, it would be possible to host these Majorana fermions. So if we can control direction of magnetization, now we can control where these Majorana states reside. You can view them a little bit like domain walls. Once we have a region where magnetization changes, we may have a presence of a domain wall. Once we have a region where topological condition becomes trivial, then this is the region where Majorana states could be supported. So by using standard control of magnetic textures in spintronics, we can now move these Majorana states around. Or if you wish, we have designed these effective nanowires, not by epitaxy, but we have designed them by using magnetic textures. However, this was a theoretical proposal, and some of these magnetic structures are not that easy to realize. So we teamed up with our experimental collaborators to see what is experimentally feasible, and maybe we can use these ideas in a slightly different platform. Our experimental expert in growing superconducting structure, Javad Shabani, can make very, very nice and sharp junctions between semiconductor indium arsenide and superconductor aluminum. Our other collaborator, Andy Kent, who is an expert in magnetic nanostructures, he actually has a small company working on so-called spin transfer torque, where these magnetic nanopillars can be nicely made, and one can change even the direction of magnetization simply by passing current in these magnetic nanopillars. So then our idea was to use again magnetic textures in 2D structures, but have a different type of array of magnets, and we can then change fringing fields from strong to weak by changing these relative orientations of magnetization. And then these fringing fields will modify two-dimensional electron gas nearby, and therefore we will have additional effect of two-dimensional electron gas being modified by the superconductor. So magnetic proximity from above, superconducting proximity from below, and there may be a sweet spot where we can create effective wire at which ends these Majorana states would be supported. This most probably the first example of using detailed micromagnetic simulations to study Majorana fermions. So we needed really not just some simple model description of this structure, but accurate calculation of the resulting induced fields and magnetic textures to realize whether Majorana states could be supported. And what is then interesting, based on these calculations, we can also predict how, for example, this effective wire with two Majorana state as at its end can be transformed. So if we have one such long wire, we expect that at its end, there would be formation of this localized but spatially separated Majorana fermions. But if we were to change direction of magnetization, now we may break this wire, and instead of one long wire, we have two short wires, and we create an extra pair of Majorana states seen here. This little bit far-fetched idea now has been brought closer to reality, because similar to our studies how magnetic textures can support Majorana states, and again more micromagnetic simulations, we've seen now that this induced synthetic spin orbit coupling was recently experimentally demonstrated in Paris. So carbon nanotube next to two niobium regions and then a cobalt platinum multilayer was supporting Majorana fermions. So basically, at least in principle, one can use this combination of magnetic and superconducting proximity effects and the role of inhomogeneous magnetic textures to design very exotic superconducting states. There is also another class of systems where we don't rely on magnetic textures, we just apply magnetic field, and in variation of Josephson junctions or squid geometry, we can even see a direct signature of topological transition. So we can see a phase jump simply by controlling gate voltages in this squid geometry. And this may be the first experimental demonstration where phase across topological superconductivity or transition to topological superconductivity has been measured in a squid geometry, which then also led us to ideas how these planar Josephson junctions may be engineered in different shapes to then host multiple pairs of Majorana bound states and then support braiding and other properties that would confirm what is the ultimate goal, which is their non-abelian statistics and ability to really use them towards topological fault-tolerant quantum computing. So with this, let me provide some conclusions. And then if there is another minute or two, I'll tell you a little bit about possible outlook. So what I was trying to argue is that many decades following first demonstration of proximity effects, we are now in a position to view them more broadly, not just as a curiosity limited to few structures, but as a systematic tool to transform large class of materials, especially if we consider two-dimensional materials and van der Waals heterostructures, then these proximity effects may play a very important role. We may need to include Coulomb interaction in magnetic proximity effects, especially in these transition metal dechalcogenides or other materials where there is a weak screening. Role of excitons is important, and single particle picture is clearly not enough. If we were to consider both magnetic and superconducting proximity effects, it may be possible to even realize Majorana fermions, and recently we were involved in direct phase measurements of topological superconductivity, which is a platform that hosts Majorana fermions. In terms of novel devices, there may be a possibility that these magnetic proximity effects could allow us to envision applications that are room temperature, but not limited to magnetoresistive effects. And we recently were working on a class of ultra-fast spin lasers where surprisingly short rather than long spin relaxation time was desirable. So if I have another minute or two, I would then mention some of these possible directions. But if we are running out of time, I can stop here as well.
Well, I think if you can go on if you have time. So if then people are free to leave. If
it will be just 2.5 slides. So concept of spin laser is just analogous to concept of ordinary laser, but we add spin polarized carriers. We can do that optically by shining light or electrically by placing magnetic contacts, and then imbalance of spin through conservation of angular momentum means that emitted light could be circularly polarized. So this is basically a spin laser in a nutshell. And what is important is that now we have a new degree of freedom. It's not just about controlling intensity of light, but also controlling its polarization. We can study this at the level of a bucket model, and if we have a bucket where we put hot and cold water, we can understand that if we have unequal amount of water that we put in, and this slit corresponds to the lasing threshold, then it may be possible, even when we have almost similar amount of cold and hot water, to see lasing or gushing out of water coming from one faucet, or in this case, one helicity of light. So laser can also serve as an amplifier of spin. Tiny imbalance in spin can be amplified to give us completely polarized light emission. But what is most exciting is the dynamical operation of laser. And my experimental colleagues from Germany were able to demonstrate that by introducing birefringence, anisotropy of index in refraction through basically deforming of their sample, they can create ultra-fast operations. So it's a little bit like beating. And these lasers could then operate much, much faster than the best conventional lasers. While best conventional lasers, when we kind of modulate their intensity, can reach 20, maybe sometimes 30 gigahertz before this response dies out. Polarization modulation in these highly birefringent lasers can be an order of magnitude higher. So there are fascinating possibilities then associated with this realization, but there are also important limitations because polarized light was used to create spin polarized carriers. So then the next question is whether we could take advantage of this very fast polarization modulation and also very low power, because we don't need, as it's usually done, to pump laser at very high power. So can we somehow take advantage of that by creating spin polarized carriers through presence of nearby magnetic material, and maybe even realize it in two-dimensional materials which have good optical properties? And then maybe as a summary, why this would matter, here is the following cartoon. So in modern computers, increasingly energy consumption is determined not by transistor, but by interconnects. So if you look at this highway situation, this is actually taken from Brazil. It may not be that important whether we have here Ford or Ferrari. It's not a problem of the car. It's not a problem of a transistor. It's a problem of a road or interconnect. And perhaps the hope is that with these ultra-fast lasers, we can then implement ultra-fast and ultra-low energy interconnects for the growing need of transferring information and communicating them. Thank you very much.
Yeah, so that was quite interesting. I had a quick question about this. So why would, for example, spin lasers be better for these optical interconnects than other lasers? Like where's the extra energy that you?
Yes. Yeah, okay, excellent question. So what is basically helpful is to identify laser with a harmonic oscillator. So if you have a harmonic oscillator, you expect that there will be some resonant frequency. Imagine that you are kind of driving this harmonic oscillator, and above the resonant frequency, its response will go down. It's a little bit like when someone speaks to us in a foreign language. If we know few words of a foreign language, we can follow this person if he or she speaks slowly. But as soon as this person starts to speak quickly, we are lost. We are unable to follow this external perturbation. So this is a property of harmonic oscillator, but this is also property of conventional laser. And there, the limitation is that intensity changes that are used in conventional lasers cannot really go above 30 gigahertz or so. And the way how they go to such high frequency relies on adding more and more power, adding higher and higher pumping. This TH is an abbreviation for lasing threshold. So you need to go to 10 times higher injection current to reach this value, as opposed to being at a much lower injection. However, in a spin laser, relying on high birefringence, one can stay at the low power of injection, and by increasing birefringence, one can effectively increase resonant frequency 10 times higher than the maximum value in the best semiconductor lasers. So in other words, we can change polarization much faster and also at much lower energy than we can change intensity of emitted light. And the polarization that comes out is connected to the imbalance between spin up and spin down.
Sure, but birefringence and changing your polarization does not always have to be related to spin, right? So you could always have other types of birefringent behavior. So why is spin so important here?
So basically, this linear birefringence can couple different helicities of light. And this coupling is then like a beating frequency. If we would try to just increase the same birefringence and see what happens to the intensity of the light will remain unchanged. So it will not be modulated. The mechanism for modulation of intensity of the emitted light is almost independent of birefringence. So it's as if someone is quickly talking to us in a foreign language. We just ignore that person. But for spin lasers, this birefringence allows them to kind of reach a resonance that can be controlled as the birefringence is increased. And here, these are basically experimental values by introducing strain or deformation of the sample. We can then make this birefringence extremely high, several hundreds of gigahertz, which also means while we stopped at 200 gigahertz, because this is now close to destruction of a sample, we don't know what is the limit. So maybe we can go to terahertz regime with a different material and different approaches. And this is, already 100 gigahertz is something that is just not possible for room temperature semiconductor lasers.
I see. Thanks. Thanks very much.
Okay, so if I understood correctly, so with this you're using just a constant pumping. So your spin population is basically constant.
So there are two things. So this is basically a hybrid scheme. These lasers are relatively standard, using standard materials where carriers are added by electrical pumping. But we don't have efficient room temperature spin injection. So spin that is needed is added by sending picosecond pulses of circularly polarized light. So if we have different methods of quickly modulating spin polarization, perhaps even from your research, that would be very interesting, because we really do not know how fast and how further we can push this scheme. But on the same structure, my colleagues were able to show that intensity modulation is much, and changes in the emitted intensity are much smaller than the polarization changes. So this is basically a fact. So there are a few challenges. One is we do not have a good experimental approach to electrically create spins, and even for creating it optically, we don't know what is the fastest way of doing it. The other concern is not easy to have a detection scheme where you can detect these oscillations at 2, 3, or even higher number of gigahertz. So part of it is experimental implementation of such fast responses, and then the other part is also detection, because state-of-the-art semiconductor lasers, they need much less sophisticated equipment, because it's 10 times or even a slower response.
Okay, thank you. Yeah, we should discuss more. Okay, but I've seen that there was a raised hand.
Mm-hmm.
Yes, I have a question regarding, you said this inversion of the band order in the conduction band for this optical part. So you have a different terms of in the Hamiltonian. Which one is playing the central role in this? Yeah.
Yes. So it's basically a combination of exchange and staggered potential terms, because what one would like to do is to I'm not sure if this music is coming from outside, or I apologize if it's disturbing anyone. But what is basically important is to make effect valley selective. So we are trying not to just do the same thing to both valleys, but isolate one of them. And so what is shown here, that in K prime valley, we are able to realize band inversion. So this is then combination of this staggered potential and exchange field, if this helps. And the staggered potential is possible because we have inequivalent atoms. So these two antimony atoms are in a different environment depending on the hydrogen or tungsten atom. They are not equivalent, and this can then give rise to these valley selective effects. What may be more familiar to people is a concept of Berry phase. So Berry phase, of course, makes important changes to transport properties, but for decades, simple equations of motion were excluding it. Once we realized that Berry phase plays a role, then it was possible to see many of those implications or changes in transport properties and topological properties by Berry phase changes. Now something similar is happening with the winding number. If we can change the winding number, then one can argue that this changes selection rule. And this winding number is one of topological numbers that we argue could be tuned even in the same structure. We don't need to go to different thicknesses, to different samples. We can control it by gate, because staggered potential is also tunable by gate. And in the next slide, you can see that depending on the value of staggered potential, we can have crossing in these k-valley bands or not. Does this answer your question?
Yes. You also showed some, did you show some experimental data? Is this realized or not?
So this is relatively recent. So this was a PRL from last month. We are trying to work with people who have some expertise with these topological materials that are interesting by themselves, because they are very robust and they have huge topological gaps. But now several modifications are needed, because this bismuthine has no direct gap and no valley effect. So we have to reduce its symmetry, and we have to make band gap direct. This is what is one possibility to realize desired scenario. So we hope that this will not just be a theoretical proposal, but that it would be experimentally implemented. However, it's still recent, so there is no, to the best of my knowledge, related measurement. What has been measured is that people, by looking at different structures, could suggest that they are consistent with the role of different winding numbers. So not on a single structure, not this tunability of band inversion, but let's say comparing bilayer and tri-layer graphene.
Okay, thanks.
Okay. So are there other questions? Okay. So otherwise, I would say, I guess we can stop here. So if I don't know, so if people want to stay, of course, if Igor wants to stay and discuss a little bit more with anyone, so everyone is welcome to just keep hanging on the Zoom call. So, but of course, so Igor, I guess it's getting pretty late over there. So it's
yeah, thank you, Mark. Just to say, I would be happy to stay a little bit more. And if there are also any questions, Marco has my email, so I would be happy to try to answer them, especially if what I have tried now was not satisfactory.
Okay, so sure. Basically, anyone. So feel free, of course, to contact Igor. You can ask my email, but I guess it's also, so you can ask me his email, but also it's pretty easy to find his email from his webpage. And okay, so I would say that we can stop this, let's say the official session here,